VoltDB architecture, some of its use cases and examples. Hopefully leave people with a better understanding of how the product is different and what it does. So starting here, what is VoltDB at a very high level? VoltDB is a SQL relational database. It is clustered, shared nothing, so it runs on a set of commodity servers. It is open source, so you can peek at the code on GitHub. It's got a focus on operations, stream processing, and real-time analytics. And it's really different than a lot of other things out there. So who am I? I was the first engineer on the project. I've been involved with most of the bad decisions we've made here. So I have sort of a lot of understanding of sort of what's worked and what hasn't, and hopefully that'll be useful in this talk. But feel free to reach out to me. I'll put my email again at the end of the talk. But if you have any questions or anything, I'd love feedback or questions. So where did this project come from? Where did VoltDB come from? Well, it started with Mike Stonebreaker and a bunch of other researchers. It's sort of a cabal of smart people. But he's certainly the most famous, responsible for Ingress and Postgres and more recently Streambase and Vertica and other systems. And so Mike and his group had just come off the C-Store research project. So they had developed this system that said, well, what if we specialize just in analytics? Could we be faster than general purpose systems? And that technology turned into Vertica, became a research and commercial success, and they're sort of looking for the next big thing, saying, sort of, if we could do this for analytics, could we also do it for operations? And so, what they did was they took a look at what was out there. They tried to understand what was out there, and sort of I got a strained automotive metaphor here, but they saw these legacy systems that were huge, the Oracles, the SQL servers, the DB2s, etc. And they're these big trucks that people have been working on for a long time. Now, there's a lot of advantages to these systems. They're very robust. They've been beaten on. There's a lot to like about them, but they're not nimble, certainly. And there's a limit to how nimble you can make these systems. So you could put another 100 years into these systems, but because of a lot of the legacy constraints, the compatibility that they need to be maintained, the customers they need to support, the best you can hope for is something a little bit weird. You can make a truck faster, but it's not ever really a race car. So what came out of this was this research. And this paper is a really fun read. It's from, I believe, 2007. If you haven't read it, it kind of gives a little bit more in depth into some of the research that I'm going to go into here. Some of the things since then have changed, but it's an interesting read. All about how to build new architectures for the 21st century, building a little bit more focus into systems that focus not on, in this paper, really focuses on transaction processing on operations. So what they did as part of this research is they took legacy-style relational databases and they put them entirely in memory, and then they measured where the system spent time. So what was actually what was the CPUs doing now that they didn't have these disk accesses? So one thing they found was that there's still a lot of buffer pool management. Even if you're running on top of a RAM disk, just managing what records are on what pages are dirty, what pages are flushed, what pages are in the log, what pages are in the general store, how indexes map to pages. These things were a lot of CPU overhead. And there's a pretty easy solution to this. It's use main memory. So, it's now 2008 in this story, and memory is getting cheaper. Meanwhile, you've got systems that are focused on analytics like Vertica, but other systems, Teradata, Netezza, and you've got even other systems like Hadoop, and Hadoop is starting to take over the world a little bit in 2008. And they're saying, well, look, analytics is going to be, this deep analytics is going to be over there, the OLAP-style queries. If you're looking at just the operational stores, these things are going to, if they don't fit in memory now, they're going to fit in memory in a few years. So let's build a system that uses main memory. So the other thing that they ran into is there's a lot of concurrency. Certainly, as we get more and more cores and more users using the system at once, there's a lot of locks and latches in the code. If you've ever looked at the code for concurrent B trees, there's a tremendous amount of complexity over single-threaded data structures, single-threaded B trees. And so there was a lot of time spent managing this concurrency, both in terms of the number of CPUs, but also in terms of the number of users that are trying to access the same data at the same time. So the answer to that is run this single-threaded. Don't do the concurrency. Don't use B trees that are not just slow, but also hard to implement, hard to show they're correct. Use much simpler single-threaded data structures. So these two things are sort of the real core. A lot of the architecture of VoltDB falls out from here. Because we end up with a couple of problems here. If we're waiting on users while we're doing single-threaded operations, if we're processing sort of one user at a time, if a user says begin transaction, runs a query, sends that back to the client, and then says, okay, here's the next thing to do, the system is basically idle while the client's making a decision. So that's not something we can accept. And the other thing is that single-threaded doesn't really work as you have more and more CPUs. So I've got a system, with 32 cores in the closet next to me here, and that's not even that high these days. There are plenty of systems now moving on to 48 cores, 64 cores, hyper-threading adding on top of that. It's really, where things are going is a very, very parallel, very, very concurrent world, especially in operations and stream processing. So what do we do for these problems? Waiting on users. And this is another way to say this in the database lingo is external transaction control. So the answer that the VoltDB and the research team before it was called VoltDB came to is don't do this. So Volt breaks with history. We don't support external transaction control. Essentially, if you're using external transaction control and you're trying to go fast, you may have already discovered that there's a problem here. And a lot of systems that used to use external transaction control have discovered that this is actually problematic and turned it off. Now, some people have smartly turned it off and figured out ways to work around it, and some people have done it and just sort of crossed their fingers that everything works. But this is something that's been a long time coming, and Volt just formalizes it. It says not even an option. So to get around that, how do you have transactional logic if you don't have external transaction control? We use server-side transactional logic. So that's traditionally stored procedures, stored processing. We move the logic of your business to the server so that we're not waiting on users. We can execute entirely in the context of the server, close to the data. Sort of a big theme in these days, 2015, is that moving your processing to the data, not the other way around, is tremendously more efficient. You have lots of data. Your processing is probably just a little bit of code. Move it. Don't move the data. We use Java for server-side processing, which is a language that's very easy to pick up. It's very familiar to most people in the Hadoop ecosystem, and so it's a lot easier to use than a lot of the traditional stored procedure languages like PL/SQL or T-SQL. So we got lots of cores. What do we do about it? Because we said we want to run single-threaded. So how does that not conflict? So partitioning is a requirement, right, for scale out. Clearly, I'm not going to run this system on one server. I'm not even going to accept that I want to run it on one server followed by a replica that follows that server. What I really need is to be able to scale my data to arbitrary numbers of servers, especially because I'm running an in-memory system. If I want 2 terabytes of memory, I probably need a bunch of servers to store that. So partitioning is a requirement. Single-threaded is something we want to do for efficiency. This is how we want to go fast. Why not partition to the core instead of the node? Why don't I treat 4 machines with 4 cores as 16 little tiny machines instead of treating them like 4 machines with shared multiprocessing? So this is really, we look at this as concurrency via scheduling, not shared memory. A lot of times in VoltDB material, you'll see us talk about how there are no locks. And what we're really saying is there's no locks while we're executing SQL commands. There is some concurrency code that manages distributing all the work to the right places. But this allows all of our data structures, all of our SQL processing to run without any locks, without any complicated shared data structures like concurrent B trees or anything like that. And this project, the research component of this lives on, which is one of the really exciting things about VoltDB. The research project is called HStore. And if you go to the HStore, if you Google for HStore, you'll find this page here with these universities, and Andy Pavlo at Carnegie Mellon is maintaining these pages. But there's a tremendous number of papers that have been published recently about HStore, variations on HStore, things you can do. So it's exciting that the research is continuing. It's obviously an interesting platform for academics. All right, so getting into the architecture of VoltDB here. How does this thing actually work a little bit? This is similar to the motivations, but a little bit more concrete. Why is this different than other systems? So as we said, we're partitioning to the core. That's different than most other systems. Most systems partition to the machine. We're serializable ACID. So familiar with ACID, it's a concurrency guarantee that relational databases typically offer, and our ACID is serializable, which is the strongest form of consistency. It's not read committed, it's not read your write, it's not MVCC. So that's something that's a little bit different of Volt. You can't actually turn that down. That's something we rely on to go fast, which is a little counterintuitive, but we'll get to that. Volt is active-active replication within a data center. So we make sure that before we commit anything that your write is to several places. No external transaction control, something we talked about a little bit before, and Java stored procedures. Just calling out that you can step through your stored procedures with a debugger, which is cool. And I wrote fast in the corner because that obviously is some way we're different. That's more of a consequence of this stuff, not the actual feature. VoltDB clustering, a little overview of how that works. Adding clustering to Volt. So partition of CPU cores. We buddy up cores across machines for high availability. So if you tell us you'd like 2 copies of all your data, we'll pair cores on different machines. If you say that you want 3 copies of data, we'll build triples of cores on different machines. And we call those logical partitions. So a logical partition might have 2 replicas or 3 replicas across different machines. We do fully synchronous replication among those replicas within a cluster so that the replicas are always perfectly in sync. We do asynchronous replication across clusters, so either to a cluster down the hall or around the world. It's an asynchronous system at this point. So partition workloads parallelize linearly. So this is something where we see a lot of partition workloads. We're going to get to a little bit later some of the kind of example workloads and kinds of things that look like Volt apps, but we find that a lot of workloads do partition well to cores. So what's in a CPU in Volt? We build queues of work that we're going to be doing, and if the system isn't full, these queues are often very, very short. But they're sitting on top of what we call an execution engine, and that manages table index data for that core. If you take all the cores and all the replicas and you stick them together, you've got one logical image, which is what the client sees. The client sees a single global database, and there, it has some understanding that this is partitioned, but it's not a system that you manually partition yourself. You don't say, on the client, I need to figure out which of the cores I need to route to. It's something that's done automatically by Volt. So we have 2 kinds of tables, partition tables and replicated tables. Replicated tables are replicated to each core. These are typically smaller tables. They're often dimension tables or lookup tables. But there are times where they're just tables that are updated less frequently than the partition data. And partition data tables are split among all the logical partitions, and they're based on a column partitioning key. So for example, if I have a set of users, maybe I want to partition on user ID. Every table that has a row that is my user ID will be on the same partition. I can join between them. I can do all that stuff. So there are 2 kinds of transactions on Volt. So there's sort of cover how the data is split. But there's 2 kinds of transactions. There's partition transactions and global transactions. And we're going to get to that a little bit, what's the difference between those in the next couple slides. Partition transactions are routed just to the partition they need. And global transactions can be read and update all partitions transactionally. So if I've got a Volt cluster here as a little picture, I've got maybe 3 machines and I've got 9 partitions. This isn't, in this case, I guess we've got 1 copy of each partition, but certainly they could be replicated. The way the multi-partition transactions work, the global transaction, is that there'd be a leader designated for that transaction. In this case, partition 5. And it would slot work into the queues of other partitions that it needs. And we've actually got a technical note going either on our website or going on our website describing in detail how this stuff works and how we support the guarantees we have. It's a little bit beyond the scope of this talk. To give it kind of another view, and some of these slides are a little bit thematically incongruous because they're pulled from a couple different presentations. But this is an example of, if I'm splitting a table called player based on player ID, I might have two players on one copy of one partition, 2 players on another partition, and 1 player on the last one. So I got 5 players total. My single partition queries, like select from player where player ID equals 1, 2, 3, I can route that because I know player ID is the partition key. I can find which partition controls ID 1, 2, 3, and send the query right there. Doesn't have to coordinate, doesn't need any special consensus except between its own replicas. I can run these queries very fast. Multi-partition query, select star from player where last name is Brown. Since I'm not partitioning on last name, I have to send that query everywhere and then aggregate. And the client, note, all I have to do is send this SQL statement to Volt. VoltDB is going to figure out that this needs to go everywhere. It's going to collect this data from all the different partitions, and it's going to re-aggregate it for me. This is not something that I have to understand from an application correctness point of view. There are some performance consequences, so from a tuning point of view, it does help to have a picture of what's going on under the covers. But from a correctness point of view, Volt does all the work for you. So what is special about Volt? I alluded earlier that this serializable ACID is crucial to Volt. That some of these tricks that we use, what allow us to go fast. A little bit more detail on that. I'm going to go a little detour into determinism and synchronous replication and talk about what Volt does. And this looks, to my knowledge, nothing like anybody else in the data management space. So, determinism. Let's say I want to run the same SQL against 2 databases, and I want to keep them in sync. So I can create a table in both databases, right? I'm storing some birthdays for different people. So maybe I want to insert a birthday for ID 1, insert a birthday for ID 2. Maybe I want to update a birthday, set that to a new year where ID is 2. Maybe I want to get the top birthday from a year by age. If I run these SQL statements to these 2 systems with empty data, I'm going to end up with the same data at the end, right? I'm going to have 2 records. They're both going to have the same birthdays. I've got sort of identical copies of things. So then somebody has twins, right? And I want to enter in new twins into the system. So how do I do that, right? Brand new. I could say insert into birthday's current date, insert into birthday's current date with IDs 3 and 4. But if you look at the clock right here, let's say it's almost midnight, right? Really, this is happening right at midnight. So I can end up with a situation where one of these servers is going to say, well, you made it in just under the wire. Both birthdays are January 31st. And the other system is going to say, oh, you know what, it's midnight, so this is February 1st, and one of them was born on January 1st, one of them was born on February 1st. And you can see now these 2 data sets have diverged. So these are not deterministic inserts. So I don't get the same state in both places. And now from this point forward, who knows what could happen. If somebody reads things and makes decisions based on reads, they could have all kinds of problems. What I'm really looking for with a deterministic system is sort of the connect 4 of database replication, right? I want to put red in slot 0, black in slot 4, red in slot 1, black in slot 6. If I do these things in the same order, I'm going to get the same board, right? There, that's what it looks like. So in order to do that in databases, I have to actually say, 2013 131 here. I have to externally generate that date and not let the database pick it based on a wall clock. So that now I'll get deterministic operations. Basically, current date is Plinko to a literal date connect 4. Plinko is, if you're not familiar, is not deterministic. You put something in the top, it's going to pop out, so hopefully on the $10,000 spot. But you don't know. It could be different if you do it twice. Connect 4 good, Plinko bad. Sources of non-determinism. The big 2 are wall clock time and randomness. If I call rand and get a random number and it's different in 2 systems, my data could diverge. If I call now in 2 systems, my data could diverge. So those are something to be avoided if you want to do deterministic operations. And depending on the storage engine, sometimes tuple order matters. So I could have if I insert these things and they're not in a particular tuple order, if they've been compacted or something, and 4 and 3 are switched on the two different systems, logically they've got the same data if I sort it, but if I don't sort it and just pull it, I might get different data. Right? If I ask for limit 1, I might get different records. And external systems can cause non-determinism. So if I'm beginning a transaction, I want to update the wind speed based on some ID, and I ping the weather association in the weather agent. I'm not sure what NOAA stands for, but if I ping them in the middle of the transaction, if I replay that transaction on two different servers, maybe the wind speed has changed. Right? I can't guarantee that it's going to be identical results. Maybe one of them times out and one of them completes successfully. So really, I can't talk to external systems in the middle of my transaction if I want this to be deterministic. So in this case, I can just ping the weather and then start my transaction. So in the transactional context, the wind speed is passed in to both systems as the same value. Okay, why? That was a little bit of a detour on determinism in databases. Why is that important for Volt? So Volt uses something called logical logging a lot. We keep a log of the operations in a fixed order, so that if we replay operations in a fixed order on the same starting state, we should get the same ending state, right? Do the same things in the same order, the same data, and if everything is deterministic and serializable and happy, you'll get the same ending data. This requires strict determinism. No wall clock time, no random numbers from the system's random number generator or Java's random number generator. No external systems can be talked to in the middle of a transaction. Now we've made a lot of these things a lot easier in Volt because we have our own calls. If you want to get the current time, we'll give you a logical time. If you want a random number, we'll give you one seeded with a logical identical seed on multiple replicas. And we've made sure our tuple order is not going to bite you. But logical logging, right? So that's something we use a lot. So logical logging, basically this relies on everything being serializable. I kind of said this in the previous slide. But this is really hard to do for a lot of systems. Almost no one runs their relational databases with serializable isolation. VoltDB sort of, some of them support that, certainly, but VoltDB does it actually as a performance trick, not as a performance compromise. So we've got the Connect4 database, right? That's what we've built. We've built the Connect4 database here. And why have we done that? Well, one big reason we've done that is latency, right? So if my log is not writing the tuples that are mutated, but rather it's writing the thing that I'm doing, I can start logging to disk or to the replica system as soon as I've agreed on an order and what I'm going to do. So I decide first what I'm going to do in what order. And then I ship that off either to disk, to another machine, wherever I need to send that logical log. I can ship that off before I do the work. So then at that point, I can actually do the work at the same time in two places. Whereas with a binary log, I have to do the work, generate the delta on the binary data, send that off to the replica, and then the replica follows me and does the work later. So if I've got an operation that takes 10 milliseconds, then I'm actually bounded. It's going to take 10 milliseconds to run on one site. It's going to take the time of the network to send it to the replica, and it's going to take time for the replica to apply that to its data. So with logical logging, I can do things in parallel just by shipping sort of an agreed-upon order in operations. Another benefit is that it's bounded size. So if the operations fit on a gigabit connection coming in, then I can log them at gigabit rates, which is nice. Of course, it again requires determinism. Another example, so why a stored procedure is nice this way is I can log the fact that you called stored procedure pizza, and I don't have to log the actual things that you've done because stored procedure pizza is fixed for that logical point in time. So when I replay things, I just say, oh, well, just call pizza again. Pizza is a deterministic stored procedure. I can actually be very efficient with my logical logging. So kind of, again, summarizing, the consensus in Volt is replicating the schedule of logical operations to all partitioned replicas. It's not doing any kind of consensus whatsoever while it's actually processing the data. So if I combine this with Volt's no user wait policy and no disk wait policy, right? We're all in memory, so we're never waiting on disks to fetch, and our transactions are all stored procedures, so we're never waiting on a user to make a decision. We basically can run at hardware speed. So this is why, Volt serializable, which really is a lot easier when you're single-threaded, but Volt serializable, Volt in memory, Volt stored procedures, Volt deterministic. These things are really the legs that the table of performance stands on, and it's what allows us to be faster than any system I've seen, dramatically in most cases. This is basically, this is the secret sauce to Volt that isn't very secret, that allows it to be really fast. And I should say that, if people are getting concerned, what happens if there's a bug or if things diverge, and do you notice is there some kind of agreement that checks that you actually are deterministic? And the answer is yes. We do a lot of hashing and various checks to make sure that the data is actually identical on different partitions in an aggressive way. I haven't gone into there. That's actually a patent that, and we've got some other docs on that. But we do take a lot of precautions to make sure that these things are actually identical, not just, we cross our fingers and hope. All right, moving on a little bit. So storage and execution. Volt is an in-memory SQL relational database that runs single-threaded partition on each core. So each partition replica has a single C++ object called the execution engine that it works with. Now, most of Volt, I would say, well over half is written in Java, and Java handles all the transaction management, all the networking, a lot of the interfacing, admin tools. There's a lot of Java in Volt, but for essentially the data storage engine stores data for long term. It stores lots of data. The efficiency in memory of C++ is a huge advantage. The control of memory location in C++, the ability of us to be kind of tricky with our placement of things in memory, and the fact that there's no garbage collection on data that largely is in the permgen in Java made us say that all data processing and storage needs to be done in C++. I mean, it wouldn't have to be C++ necessarily, but in a systems language that doesn't have garbage collection and allows you very fine control over memory. So it stores data. It executes optimized plans generated from SQL. There's a lot of the interesting bit here is in the planner. The planner is fairly traditional, taking a SQL statement and generating a plan to execute it. It's a little different because it's partitioned, so it needs to understand that data might be in lots of places and it might have to re-aggregate it. But this is sort of the most straightforward part of building VoltDB. It looks a lot like other systems. What's cool about our storage layer? Besides the fact that it doesn't have garbage collection issues that some Java systems have, and it's very, very space efficient, it's not that cool. Boring is sort of a goal when you're dealing with storing somebody's critical data. So that I like boring for this. It's less code than you'd expect. That falls really out of it being single-threaded. Partly out of a lot of the times we've added code, it hasn't really brought that much of an advantage. For example, the different indexing types we've tried, for the most part, we find that red-black trees tend to be, kind of a good bet in most cases. We haven't added 6 different kinds of indexes. We may add more going forward. Things may get a little more complex, but there's a lot of simple code here, which we really like. It's very straightforward. There's no locks or anything on it, so you don't have to worry about concurrent access. So it's very readable. There are definitely places it could be better, but it's not as challenging as certain things. Rows are always a fixed width. This is something that we go back and forth on whether it was a good idea. I think we're settling on that it was a good idea now that more people are starting to build in memory systems, and we can look at kind of what they do and how fast Volt is and how memory efficient Volt is. Rows are always a fixed width. That means if you say I've got an 8-byte integer, it's always going to take 8 bytes. It's not going to be shorter if you're only storing the number 5 in it. Blobs and strings are stored out of line if they're over 64 bytes. They're stored in various pools that are fixed by size. It's surprisingly storage efficient. It feels really wasteful sometimes when you've got the number 5 taking up 8 bytes, or maybe you've got the string hello taking up 60 bytes because it's in a varchar 60. In practice, the overhead of managing buffer pools, the overhead of doing a lot of the different things that the alternatives to this tend to use more memory. I think that we could certainly do this and use less memory. There are a lot of things we could do, but that the sweet spot here, the balance of performance and memory efficiency seems to be really, probably we got lucky a little bit here. So that there's fixed width also means less code in a lot of places. And we also do aggressive compaction. So for example, in indexes, if you remove something from an index, we will actually go in the tree, find a tail item in the tree. Sorry, not a tail item, but find something that's in memory at the end of the tree memory structure, and then relink it into the memory of the old thing that you removed, so that the memory is completely contiguous in memory. It feels like that should be a cache miss problem, but it turns out it's not that much slower. I think that the relinking compared to the walking of the entire tree is not that much more overhead. And then you do have the advantage of everything is very compact in memory. You don't have lots of holes all over the place. And so that's something that allows us to be, we think, very, very efficient in terms of our memory usage. And the C++ storage engine is 100% open source. All the code, you can read it. You can submit bugs to us. You can tell us, hey, this is fancy. Whatever feedback you have, or whatever curiosity you have about that, you can satiate. One thing we're doing that's kind of cool is we're working on an LLVM JIT. So that's something that is coming down the road. It doesn't help in a lot of places, but it does help in queries with more complex predicates. It can help a lot in those cases, especially on scans with complex predicates. So as we get into the more comprehensive analytics support, that's something that's cool. So kind of an important point here, this architecture, sort of wrapping up the architecture bit, Volt is not a traditional relational database sitting in RAM, right? So if you ask, why is Volt different than ×10? Why is Volt different than SolidDB? Or other systems that are just sort of legacy systems tuned for RAM, so far, hopefully, I've answered a lot of that. It's weird, it's new, it's exciting, because the external transaction control doesn't work well with Hibernate. So that's sort of, it sounds like MemSQL, Nuo, Clustrix, HANA, whatever the flavor of the month is. And I'm not saying those systems are bad necessarily, but what I'm saying is they're different. They do different things well. Volt really does, I'm going to kind of get into some of the apps coming up. But it's not the same architecture as these systems. These are not like, MySQL and Postgres, where one of them, Postgres certainly has a fantastic implementation, but it's not where they're doing sort of the same things but slightly different implementations. These are really different architectures fundamentally. How fast is it? I put this off kind of a bit, so just to get people to understand what we're talking about. On the laptop I'm presenting with, I can easily do 1 million SQL statements a second and over 100,000 transactions a second. That's actually pretty conservative. I've done many hundreds of thousands on this laptop, depending on what kind of transactions they are. On a modest 8-core Intel server, these servers are now several years old, but they're sort of our benchmark reference machines. They're old Nehalem Xeons. We can easily do well north of 1 million SQL statements per second, and well north of 100,000 transactions per second using synchronous disk durability with latency around a millisecond or two. So that's sort of the thing that I'm not aware of any other system on the planet that does synchronous disk durability, synchronous cluster replication, and extreme performance at the same time. And I want to talk about, sort of this is leading into a little bit of the cloud stuff, but, we've done a benchmark on the Yahoo cloud serving benchmark, and our numbers are absolutely, bashing other systems. So it's a really, basically this is a very cloud-friendly architecture. It runs on AWS. We ran this benchmark that compared AWS and SoftLayer. AWS, I think we've got some tuning to do. SoftLayer was really easy to use. One of the nice things about SoftLayer is you can get a lot closer to the metal. And I think for some of these benchmarks where you're doing a tremendous amount of I/O and sort of coordination of messages, for these kind of workloads, a lot of the bottleneck is networking and coordination and less on the actual data processing. Because a lot of these sort of NoSQL benchmarks don't do a lot of data processing, mostly puts, gets, and simple queries. So in these cases where you're network-centric, the SoftLayer system, because it's a little closer to the metal, really ran away with it. So that was an interesting result for us, and we've been talking to the Amazon people about things we could do better, but they're a little bit opaque, and also talking to Softlayer people about ways we can go even better there. But this slide kind of just says, like, this is not a database you need to run in a back room. This is something that's very cloud native. Most of our customers, certainly not all, but many of our customers, I don't know, maybe it's 50-50, are running in various public clouds. So getting a little bit into the consequences of the architecture, what we've learned selling this thing, what we've learned kind of over the years at Volt. You've got kind of all four logos I've lived through here. What's sort of the market for this kind of thing? What does it do? MySQL can't do it, right? If MySQL can't do it, then certainly, if MySQL could do it, it would be doing it. It's not for analytic relational databases. Some use case that a pure analytics store can't do. It's something that pure Hadoop can't do, right? But it's not just scale for MySQL, right? We don't do sprawling apps built with Hibernate. At least we don't do them without a lot of work. And we don't do real, websites where almost all of it is reads and there's a little bit of writes, right? And what you're mostly dealing with is caching problems and scaling. There's no reason you couldn't do that with Volt. We have a couple of use cases that are mostly writes that are replacing sort of tiered caching systems with just one system. But it's not certainly I don't think it's our sweet spot. So what's left? Really this idea of fast data. So big data has been all the rage for a while. Fast data is this idea of capturing the data as you're ingesting it, right? If you've got big data, then obviously you've got the data came from somewhere at a pretty high rate, right? If you've got a kilobyte a day, you're never going to end up with big data in your lifetime. So you've got some huge pipeline of data, and a lot of times people are just capturing that data for later processing. Fast data is the idea that I want to actually process it as I ingest it. I want to understand it as it's happening. I want to get value from my data in real time, not in batch mode. So what is fast data? Digital ad tech, smart devices for Internet of Things, sensors. We do a lot of meters and kind of sensors and things with VoltDB apps. There's some financial data, financial exchange streams, a lot of that sort of, there's people do that kind of thing with Volt where they want to process big streams of ticks and various things. Telecommunications is a big market for VoltDB. We do a lot of call data records. We do a lot of security, authentication and things for telcos. Online gaming is another big use case. These are kind of, online gaming has a lot of sort of operational workload, but it's really important to keep the costs down. So that's something where a cloud native, very scalable system can help. So what are the things that these apps are looking for, right? So high write throughput, we knew that going in, right? Volt is really just, it's write throughput. Partitionable actions. These things, for the most part, the high volume stuff in these systems partition really well. So we knew this stuff when we designed the system. What kind of caught us off guard? People really want global live understanding. They don't want to just process these things in parallel. They want to see what's going on globally. What is my global understanding of my processing? And that's something that we had to really address, as we went to market. The other thing is that people really want long-term storage of this data in HDFS or in an analytic database. So we've added features to make Volt part of an ecosystem where you can really integrate well with these other tools. So under the global live understanding, the things we added live materialized views for live aggregation. VoltDB is one of the easiest systems in the world to do counting, mins, max, distinct sets, grouping by time windows. We make that really easy to do declaratively with SQL. And these are not, Oracle materialized views. These are sort of live materialized views that are transactionally updated with every tuple we process. We added index support for ranking functions, so not just top 10, but show me the 10 people above and below this score. We added function-based indexes and sparse indexes. I don't think it's even on here, so you can index just where there's a where clause. We added HTTP JSON queries, so you can build dashboards really easy. All of our examples use HTTP JSON to draw dashboards. And we added full SQL support for operating on JSON docs as column values. This is similar to what Postgres has done. We have update support in Volt, a little bit beyond what they do. But you can index inside of JSON documents in Volt. There's a lot of really cool things you can do with that. In terms of long-term storage, we added snapshots to CSV or to HDFS, so you can take a global transactional snapshot. But we also added this feature we call export. Export is a push technology where you push out of Volt instead of pulling, and it's designed for very, very high rates of data migration from VoltDB into something else. Export looks like write-only tables in your schema. Each table is essentially a persistent message queue. Whenever I put a tuple into a table from within my stored procedure or using SQL, that tuple is going to be two-phase committed essentially into HDFS, CSV files, JDBC, HTTP. We got Vertica working on a couple of other connectors for different people. All right, so this is another thing we learned. There's a lot of people who want to use VoltDB for processing. So stored procedures versus sort of Storm or other streaming kind of systems where you want to do some processing on each tuple as it comes in. Volt is sort of RPC style. It's certainly not RPC in the sense that it hides that you're using a network, but it's sort of that whole method signature, call things, and get an answer, right? So you get either an answer or you get an error result when you make a call to Volt. And that's different than Kafka or Storm where you sort of drop something in and maybe you get an ACK. But you can actually return results from the call to the caller from the processing immediately. You can store results directly in VoltDB state, so the state is integrated with the processing. This is different than Storm or a lot of the streaming systems where the state and the processing are sort of a little bit detached. Results, you can use VoltDB export to move data into a downstream system. And one thing that's different, though, is that Volt doesn't support complex topologies of processing nodes without a little bit of work. It's mostly the client calls a stored procedure, that procedure runs to completion, does whatever it has to do, and returns a result. So what do Volt apps smell like in this case? Distributed ingest procedures, process new info from a stream. Whether that, whether you say stream processing or whether you say OLTP, these are similar. They look similar in practice. They do a lot of read and modify partition local state. They might export data, and procedures all incrementally update indexes and views so that they can make analytic queries faster. And then so those are sort of the distributed side. The global side is that I can leverage the pre-materialized views, the indexes that are built in the partition side. I can globally query those in milliseconds and then re-aggregate them and get understanding in milliseconds, in live time. I can get understanding of what's going on in certain time windows. What are the how aggregate by certain groups, counts and volts are just. It's really easy to build these things and get global understanding. That's also transactional and ACID. So, but to stress this a little bit, what you see is a lot of distributed writes and global reads. We do support global writes. The throughput for those is typically in the thousands, not in the not higher. And the global reads, typically it's in the tens of thousands, sometimes as high as 50,000 global reads per second. And the distributed reads or writes are the things that we scale to however big your cluster is, millions upon millions. So example, maybe I've got a smart meter, right? And I want to update the reading for my smart meter. And while I'm in the process, I can calculate my balance based on personal history, and I can look up some data about what's going on. I can send that back to the meter, so the meter always knows the current balance. In terms of globally, I might want to serve a dashboard of power use by community to somebody who's looking at managing how they're generating power based on use. So, kind of to summarize some of the things we've learned, when things get really fast, right? Apps that need Volt. Nobody wants a black box state. They don't want to just put and get things. What they really want to do is understand how things are changing. They want to be able to run these analytic queries in real time as they're running all of their ingestion and all their processing queries. The difference between OLTP apps at really high velocity and stream processing apps is really small. If you look at sort of the code you write and the way we end up using things and the best practices, they start to look really similar. And we've been saying this for a while, but other people are starting to say this too. There's a lot of people who say, well, I can run my OLTP system as a log, and absolutely, sure. There's a lot of cool things you can leverage with Volt because of its strong consistency, where maybe you don't have to go as extreme. But we see this blending together too. Move the processing to the data, right? Integrate state management and processing. When the processing is in one system and state management is another, there's a coordination overhead that's expensive and painful. And then if you have a fast stateful core, adding features to that is easier than reinventing the wheel. I say this sort of, I can make this argument is a long argument, but in the batch world, in sort of the Hadoop ecosystem, where everything is sort of working on fixed data sets and processing them into new data sets, there's a real argument for specialized tools, experimentation, for everything has a specific job, and you can strew together many, many different systems to kind of process your data. In the streaming OLTP real-time space, the more systems that temporarily own your data, the more complexity that your app has, and the more things that can go wrong, the more interdependent failures you can have. Really, you want your data to move through as few systems as possible, and it's sort of the opposite of batch processing. Integration, while it's not without downsides, integration has a lot of upsides in terms of building apps that do real-time stuff. What does it look like here? So I'm gonna go a little bit quicker here, so I can finish not too late. But there's a stored procedure, there's Java, there's SQL, and there's state. You can query the state directly using SQL. We support JDBC, ODBC, REST, lots of different drivers. There's a command line tool to do that. You can also deal with stored procedures as sort of an input response, and then an export to HDFS, OLAP, CSV, and this stuff. This picture sort of is sort of the programming model of Volt. Usually, most apps are a combination of both, sort of legacy SQL against the state, as well as the sort of distributed processing. So compared to Storm streaming, this is integrated in Volt. It's not integrated in most streaming systems. They're two different systems. Maybe they're Storm and Cassandra, Storm and Redis. They're two different systems. You don't get response data with a lot of the streaming systems. That's something that's new. You can't just run a SQL query on your Storm. You could sort of run a SQL query on your Cassandra. It's not real SQL, but there's some of that. But you can't run a SQL query on Redis. You've got to write something a little special. Because I can just connect a tool to this, there's some advantage there. And again, there's no fancy topologies in VoltDB. So what's so great about this integration? For one, that from within the stored procedure, the state access is global. So there's certainly performance optimizations that you can get into with partitioning global, but you don't ever have to think from a correctness point of view. It uses very standard SQL. We've added some extensions like upsert and JSON. It's consistent, ACID. You can program like you're alone in the world. You don't have to worry about what if someone else is doing the same thing at the same time. You just don't. And then the synchronous intercluster HA is different than a lot of these other systems. We also build tools to make building apps easier. Native aggregations, like I say, the live views. Fully SQL integrated. So the easy counts, ranks, sorts. You've got lots of examples you can take a look at that do these things. You can also leverage existing Java libraries, right? So you can use, I've got an example that uses a hyperlog library. I'm going to go into that in a second. So some examples. And just a little detour here on some of the examples are sort of backing up this argument that strong consistency is helpful. And Google has really got our back lately. So here from the F1 paper, we've got designing applications to cope with concurrency anomalies in their data is very error-prone, time-consuming, and not worth the performance gains. Also from the F1 paper, which you can Google for. Features like indexes and ad hoc query are not just nice to have, but absolute requirements for our business. Millwheel, which is our stream processing system. By allowing users to focus solely on their application logic, this kind of programming model allows users to reason about the semantics of their system without being distributed systems experts. We could not agree more with this stuff. Like, we want to build things that anybody can just start using and get extreme performance out of and get correctness out of. So I got two examples here. The voter example is about counting is hard. This is very much like sort of an American Idol style reality show where I've got N contestants and people are voting over the phone. I want to count how many votes per contestant. Option one, I can just accept inaccuracy, right? Maybe I don't know how inaccurate I'm going to be, but I'm just going to build a system that doesn't really care. Option two, I can buffer batches of votes for a while and amortize the cost of using external locks. So I can have kind of different pools of votes that are distributed. and then I can kind of re-aggregate those periodically and do counts on them to get an idea of what it is. Essentially, I can build a really complex app to count things, which people do all the time. In Volt, I can support isolated atomic read then update for fault-tolerant counters. I can do this at extraordinary throughput. So what does the stored procedure look like? Essentially begin procedure, phone contestant, atomically increment the votes for the contestant by 1. I don't need a procedure to do this. I can just send a SQL statement. But this is sort of the example here. If I want to add to this, right? So I'm add a new rule. Allow each phone number to vote m times. In my procedure, I can check how many votes a phone number has. If too many, return with an error code. Otherwise, atomically increment the votes for the phone number. So that's something that is even, you can do it with compare and set. It's even easier to do in Volt, but that's sort of, if your system supports compare and set, that's great. A lot of systems that do there's a tremendous performance hit. There's basically zero performance hit to doing this in Volt. Allow each phone number to vote n times. Now say I want to, and I've got that sort of procedure logic, and I figured out how to do that with another system. Maybe I want to allow phone numbers of people who've signed up for the email to vote twice as many times, right? So I need to have that list somewhere in my state. I can look that up in Volt. Maybe I don't want to allow people to vote twice in the same minute. Send a user an SMS after their third vote, but don't send 2 of them. It's not possible 100%, but you can do a pretty good job. It's certainly easier in Volt. Provide a live dashboard of contestant scores by geography. Record votes past the limit, but don't count them. So going back, all these things, changing the Volt stored procedure to support these things is really as simple as writing, kind of CS 101 code to make these things happen. You don't have to worry about, what kind of consistency model, if you have different consistency model, what kind of problem I'm going to have if people try to do 2 of these things at the same time. Unique devices example is another example. So if I've got a real user, here's Ed who works at Crashalytics. They've got, now it's over 1 million, but this is a talk he gave about 6 months ago where they had 800,000 events every second. And what they're doing is they've got mobile applications, and they want to know how many unique devices open up my app today. And they want to provide users with a dashboard that says 87 unique users have opened up your app. They built this stack, Zookeeper, Kafka, Storm, and Cassandra, to sort of do the fast data piece of this, right? They're coordinating with Zookeeper, Kafka is doing ingestion, Storm is doing processing, and Cassandra is managing state. They're using hyperloglog, which is a probabilistic data structure. You don't have to understand how hyperloglog works, although reading the paper, it's really fascinating, or reading a wiki page or something. It's really cool stuff. But it allows you to by leveraging some Java code and a clever algorithm, you can trade off some accuracy. So maybe you get bounded 99% accuracy, but you've got O of 1 space-time, a couple of kilobytes stored in the system. And so this is something that really is not possible to do performance-oriented SQL to do this. I can't write this app in SQL. I need to use third-party code with an algorithm. And so in Volt, I have a stored procedure that's called count device estimate. My app can send a unique ID, 87, and app ID 87, device ID 12, and it can update an estimates table with that code. So I'm not going to go over this code exactly here, but this code is in our example. So if you download the VoltDB kit in the examples folder, it's all there for reading. Basically, I can write code that's about 25, 30 lines. It says input an app ID, get the hyperlog log from state if there is one, create a new hyperlog log. If the hyperlog log for this app exists, load it up, update the hyperlog log bytes with this device ID, pass as a parameter, and then update the state for the app with new estimate and hyperlog log bytes. So again, this code is all easily downloadable from our website. And I kind of reveal it here. It's about 30 lines of code to do something that the Crashalytics app is substantially more code. They do a lot of other things. I think that they've been very successful. I'm not trying to criticize Crashalytics. I think they've done some great work. I'm just, this is an example of sort of doing this kind of operation with really, really simple code at scale. So what does strong consistency enable for this app? It enables read then write of hyperlog log bytes. It enables atomic updating of new hyperlog log bytes and the current estimate. So instead of just updating the hyperlog log bytes, I can actually put the current estimate I've computed with the hyperlog log as an integer directly in the row. What that allows me to do is query from standard SQL from my clients. My clients don't need to know that hyperlog log is even used. I can write SQL to get a top 10 answer that can just query directly from the table. All of the hyperlog log functionality is completely abstracted by the single stored procedure that does this work. If I wanted to, in the variations, I could switch this stored procedure for a stored procedure that kept an exact count up to 1,000, then use the estimate value. That's really difficult to do without strong consistency. I could do rollover estimates into a separate table on a periodic basis, right? So every night at midnight, if on the first time you run the procedure at midnight, after midnight, I can move that yesterday's estimate into a new table. Without strong consistency, it's hard to know I'm only doing that once. But I should say it's not that these things are only doable with strong consistency. It's that they're so much easier to do with strong consistency. It's also not just, hey, you've got less code, right? Like, it's great that I've got 25 lines of code. It's that this code is easier to verify. I can make an argument that this code is correct, and if this code was 1,000 lines of code, it gets a lot harder. A side note here that I think is really interesting, especially with VoltDB, is idempotency. The idea is that if your operation is idempotent, it has the same effect no matter how many times you do it. This is really important in stream processing because sometimes you send something and you don't know if the other side got it. If your system is idempotent, you can just send it again, and if it gets it the second time, it acknowledges it the second time, you know you're fine. If it's not idempotent, then sending it the second time might actually corrupt your data. So in this case, the unique devices app is idempotent, right? Sending the same device ID repeatedly won't change the estimate. This case is a little bit trivial, but a lot of the strong ACID consistency makes idempotent really, really easy in a lot of applications. I just built an idempotent processing app that processes Kafka streams for a customer, and it's just tremendously less code than doing that with other systems. A lot of times I can just change inserts into upserts, and magically it works. VoltDB, though, one catch, we enforce no side effects, right? So you can't call out to an external system. You can only modify VoltDB state. The only thing that's actually guaranteed to be consistent is the VoltDB state. And so that's a limitation. It's what allows you to make things in idempotent. But as soon as you start mixing multiple states together, then idempotency is really hard to do. And just, on the left here is the format of the kit you download. If you download the VoltDB kit, you'll see there's an examples folder, unique devices, and all the code is in there. The voter example and all that code is in there. There's examples of doing voter with JDBC. If you download our other clients, you can see voter in C++. Lots of examples to take a look at this to further explore. All right, I want to wrap up. I'm going to do this last bit quickly here, so I kind of come in a few minutes over an hour, but about an hour. Where's Volt going in the future? So certainly there's the boring, obvious stuff, right? More integrations with other systems, more SQL, administrative improvements, right? Our admin tools continue to get better. We've released a brand new admin tool called VMC earlier this year, and we're really expanding the functionality of that quite frequently. More examples and walkthroughs, making it easier to learn how to do certain things in Volt. These are all sort of the boring, obvious future. But I will say that for our customers, it's like the greatest thing. That we have every time we implement some new SQL feature, we go through our backlog and say, here are the customers that are going to be really excited about that feature. And we send it to them, and they do a little dance. So the stuff, it's not exciting at a high level, but actually using the system, this march of progress is something that's kept people very happy. Non-Volatile Ram is interesting. I can't say much about it. One of the most interesting things about it is that lots of people talk to us about it because we're an in-memory system, and we sign NDAs with everybody. So I can't really share what I know, not just with outside audiences, but with the individual people who are talking to us about this. It's a very weird situation, but it is something that's very interesting to Volt. It's coming. I don't know when, or if I did, I couldn't tell you. But it's interesting. Easy active over WAN. I think I'm going to finish up on this and kind of skip the last bit. But this is something that if someone promises this, then they're fooling you. You're wrong. It's not a thing. But it is active over WAN is something that a lot of really big systems at scale, they have to deal with, right? How do I deal with this? What are some strategies? So first of all, it almost always means asynchronous because people aren't willing to pay the cost to synchronize over WAN. If your data center gets hit by an asteroid, you might lose some work today with VoltDB or with a lot of these systems that are asynchronous, but people aren't really willing to pay 30, 40 milliseconds to synchronize with across the country. So starting with asynchronous active, what do people do? You can do all writes, no updates, perfectly commutative, ideally idempotent, right? These kind of things, you can do these in two different places and typically merge them, right? So you got logs of actions, right? This thing happened, capturing immutable events, tweet streams. If I tweet in California and it goes to the California server, and I tweet in Boston, it goes to the Boston server, and these are partitioned. When they rejoin, I can just merge the tweets together, and that's my tweet stream. It's not a problem. That's one. If you can do that, then great. Two, data is grouped. So maybe it's by customer group, team, whatever. Every group has a master cluster, and writes go through the master cluster. You can use Zookeeper for mastership transfer when things go wrong. If it's granular, you can use people to say, oh, I'm going to fail over manually. Data centers don't typically fail often. They do fail, but maybe a few minutes of someone with a cool head deciding, yeah, this really failed, is worth the cost of automatic failure detection messing things up. Depends on your app. But that's something that people can do. You can get asynchronous active that way. So for example, if I've got New York City, Rome, and Hong Kong, all my data is in all cities, but if you're a user in New York City, all your writes go through New York City. If you're a user in Rome, your writes go through Rome, et cetera, et cetera. Queries in Rome might be reading slightly stale data about New York City or Hong Kong, but that often is acceptable. There's a variation where the client controls the master cluster, so the client writes, client Rome writes to Rome, but if Rome isn't available, the client just starts writing to New York. In these cases, they're often a little bit simpler to build, but maybe you lose something. It's really, you don't want to say, I can never lose anything ever. I mean, that's weird coming from the consistent guy. What you want to do is you want to say, what's the worst thing that I might, what's the cost of all these things? And so, if the frequency of a data center failure is low enough, and the amount of things you're going to lose, or the value of things you're going to lose is low enough that's cheaper than building a perfect system, then people do that all the time. If you need a perfect system, you can do it, but it's work. The third way to do it is just to kind of not really think things through, and a lot of people who ask for active probably fall into this category. It's something that can really, if you don't think this through and decide how you want to do this, conflict detection, these kind of things, they can really cause problems with your data. So I was going to talk about Big Iron, but I'm going to kind of skip this for length a little bit. Big Iron is interesting because we've got lots, even more cores and NUMA and things. And just to kind of skip to the point, one of our solutions for Big Iron is to run a process per socket, pin processes to sockets. Turns out this scales a lot better than running one process across lots of sockets. Since Volt's already partitioned, you're fine. The real work here is providing admin tools for users to do this, and for having VoltDB replica placement understand this and send it to, and not keep your data on replica on the same hardware as your primary, etc. So a little quick there, but certainly wrapping up. Data center awareness is also something interesting that we're working on. Various operating systems for data centers, various packaging systems for data centers, different clouds, being native on those, different, working with VMware. There's a lot of interest in how you manage clusters of clusters of clusters like nowadays. So that's something that also is in the future. So that's my talk. It was a little bit, roughly an hour. I really am interested in feedback. If something didn't work in this talk, I know I went fast for some of this stuff. I'm really happy to answer more questions to go into work thing. If something didn't land in the talk, if you said that can't be, or I didn't understand, that would also be really great feedback. And if you want to tell me about your data management pain, things that drive you nuts about some problem that you have, I'd love to listen. We're always trying to get more feedback. And if you think something is cool, I'd love to know about that too. So thanks a lot for listening. I know Romeo's been running this thing, and thanks a lot to Romeo for running this meetup. If you want to feed me questions, I'm happy to answer questions. I don't know if I can see them.
Hi, John. So first of all, thanks a lot. It was an amazing talk. So since we are not too many, I just suggest, in case you are willing to ask a question, just hit *6 and then you'll